Finish up 11.1 and 11.2 today. Reminder, your worksheet for chapter 10 is due Thursday. This Thursday I say by midnight, but I'm really not going to look at them until the next morning. So do in the middle of the night if you're a late nighter. So Thursday for chapter 10. One thing I wanted to show you before we sort of do more math here. On Thursday last week, we talked about these Taylor polynomials and how a Taylor polynomial is really an extension of the concept of a tangent line. A tangent line is the best linear approximation to a curve. P sub 2 is the second order Taylor polynomial. That's the best quadratic approximation. P sub 3 is the best cubic approximation, etc. And so the idea behind the Taylor series, or a Taylor polynomial, is that it's a better and better approximation. And if we take a look at this Desmos thing here, I've got a picture of sine x. There's the Taylor polynomial for sine x right there. And this will adjust the power on it. And you can see right now that the best linear approximation at the origin is the line y equals x. And then as we go further out, there's the best. If you look at the power on this Taylor polynomial, it's a 2n plus 1. So when this n is 1, it's the best cubic approximation. You'll see with sines and cosines that sometimes powers disappear, so this power is always odd for this Taylor polynomial. So, and you can see what it does. It just as you go out, so it's going to turn out that the Taylor polynomial for sine or for cosine or for e to the x, they will have something called an infinite radius of convergence. And so it will just continue to wrap. If we use the entire series, it will actually equal the function. So instead of stopping at capital N, if we go to infinity, this would become a Taylor series instead of a Taylor polynomial, and it will actually equal the function everywhere. It will exactly match the function. If we truncate it and just look at a Taylor polynomial, it's going to match really well centered at whatever the center of the Taylor polynomial is. This one's centered at 0 because it's not x minus anything. So it's centered at 0. And similarly, if we look at other functions, if we look at the exponential function and its Taylor polynomial, same idea. The best linear approximation is right there. If we go out one more, there's the best quadratic approximation, and etc. Best cubic, quartic, and it's also going to have an infinite radius of convergence. It converges very fast over here on the right, and it will eventually converge here on the left. This one gives you a good visual on why you might not want to always use 0 as your center. If we're trying to estimate something out here, we would have to go very far out in this Taylor polynomial to get accuracy this far away from a center. Whereas if you move the center, you can go less far out in the series. So that's why we might want to have a different center. Oops. Let's see. So that's not what I want to be doing. How do I move that there? So here is inverse tangent. Right there. Inverse tan, we've seen that function a lot. Here is its Taylor polynomial. And let's go down to here. So there's the best linear approximation to inverse tangent. Also y equals x, just like sine of x. It's the best linear approximation at the origin. And then the best quadratic, cubic, etc. And it just keeps doing that. Now with inverse tangent, what you're seeing is that it's not getting further and further out in the series, along the function. The radius of convergence for inverse tangent is going to turn out not to be the entire real line. We're going to have a limited interval of convergence. And so it cannot go beyond these. There's going to be asymptotes right here that will not allow convergence beyond 1 unit from the center. We'll talk about why that might be later. So not every common function is going to have a Taylor polynomial that has an infinite radius of convergence. It's going to be sort of, some of them are going to be narrow. Here's another important series that we're going to look at, an important function. We've already looked at it. It's the corresponds to the geometric series. And this function 1 over 1 minus x. So there's the best linear approximation, and we're going to see here that we have something similar to inverse tangent. It's never going to get beyond -1 no matter how far out we go. The interval of convergence here is going to be, again, 1 unit in radius, 2 units wide, just like it was with inverse tangent. So not every function is going to have an infinite radius of convergence or an infinite interval of convergence. So let's take a look. There's the exponential function again, same thing we just looked at with that Desmos visual. So this says find the Taylor polynomials P1 through P5 centered at 0 for e to the negative x. So last class we found P sub 1 and P sub 2. We found the best linear approximation, which is P sub 1, aka the tangent line. And we found the best quadratic approximation, which is P sub 2. So now they want us to go all the way out to P sub 5. So let's go ahead and do that. So we're going to use the same pattern that we used last time for the, that's not what I want. That's what I want. We're going to sort of set up I like to think of it as a spreadsheet or a table. And we're going to start with the function and its derivatives. So, and I usually will use y because it's just a little less writing. So we start with that function. And if we're going to go all the way out to P sub 5, how many derivatives are we going to need?
4.
So we'll take 4 derivatives. We'll get down to the 5th derivative. We're going to go to the 5th derivative. So just like with the tangent line, we need the first derivative. So P sub 1, we need the first derivative. P sub 2, last time on Thursday, we had to get the second derivative. So P sub 5 will be the 5th derivative. It's always going to match. So let's go ahead and take all these crazy derivatives. Not too bad for this function. We just do repeated multiplication by -1 because the derivative of the exponent is -1. And then the 5th derivative will be negative e to the negative x. So there's our first column, if you will. Want that. These. There we go. Okay, so first column is the function and the derivatives that we need. If we're going to P sub 3, we'd have to go down to y triple prime. Now we want to evaluate each of these at the center that's been selected. We're told that we want to expand this function around the point 0. So that's our center. So we are going to evaluate each of these at 0. E to the negative x at 0, 1. And then y prime of 0, -1. Y double prime of 0 is going to be +1. Y triple prime of 0 is going to be -1. So we get this alternating pattern. And the 5th derivative at 0 will be -1. All right. So start with the function and its derivatives. Evaluate each of those at the center. If you just keep things in columns, you should be okay. Now we're going to build. So P sub 1 is a function, and it's going to be a linear function. We start right there, y of 0. Start with the value of the function, and then we have -1, so that's the slope of the tangent line, and then we multiply by x minus the center. Center here is 0, so we could write this as 1 minus x if we're sort of simplifying it. And when the center is 0, you do not have to write x minus 0, but that's what you should at least be thinking in your mind. If the center were 2, you would put in an x minus 2. It's always x minus the center. So here's your tangent line. And then P sub 2 of x It's going to be p sub 1. Okay, so we still have that p sub 1 piece, but then we're going to add the second derivative, and here's where it gets a little funny, but then we have to take that second derivative value, and we did this last time with the quadratic approximation, we have to divide by 2 factorial now. So we have to modify that by dividing by 2 factorial, which is just 2. And then it's going to be x raised to the, what power? Second power. Exactly. So there's p sub 2. That's the best quadratic approximation. That is the second order Taylor polynomial. Keep in mind that the order of the polynomial does not match the number of terms. There's always one extra term if there's no coefficients of 0. Right, so second order means you have a trinomial. Right, you have 3 terms. This linear, you have 2 terms. So there's always that constant term that is sort of in front. And then p sub 3 is p sub 2. It's p sub 2, and now we add a third order term. So we're ratcheting in the accuracy by adding an extra power, an extra derivative. So now we're coming down here to the third derivative, that's minus 1. So it's going to be minus 1 divided by 3 factorial. That's our pattern. 3 factorial, and then we're going to have x minus 0 to the 3. That is our third order polynomial, third order Taylor polynomial. That's the best cubic approximation to e to the negative x at the origin. P sub 4 will be p sub 3. So we just kind of come down here. You don't have to simplify this. This is easy enough that we can. Now we go to the fourth derivative. So p sub 4 will stop at the fourth derivative. We get plus 1 divided by 4 factorial is our pattern. And then x minus 0 to the fourth. So there's the best quartic approximation to e to the negative x at the origin. And we're going to go one more. P sub 5. P sub 5 of x is p sub 4. And we have our p sub 4 here. What's that, 1 over 24? And then we go to the fifth order derivative. We get negative 1 divided by 5 factorial times x to the fifth. And that is our best fifth order approximation. That's going out pretty darn far for a Taylor polynomial to the fifth order term. Any questions on any of the steps? So the coefficients, remember that the coefficients, oh, it was here. Coefficients are always going to be the kth derivative divided by k factorial. Those are the coefficients all the way through. Now let's try another one. Let's try one that's not centered at the origin. So we're going to find the Taylor polynomial for cosine of x, but instead of expanding around the origin, we're going to expand around the point pi over 6. So in our mind, we're imagining being over at pi over 6 to the right of the y-axis. That's where our center is going to be. That's where the wrapping is going to start happening to the function. So they want P4 and P5. We start with our function, y equals cosine of x. If we want P5, we need to go down to the fifth derivative. So let's start happily differentiating. We've got to get all the way down to that fifth derivative. All right, so now we have our 5 derivatives. Step 2, column 2, we are going to evaluate each of these at the center that we were told to use. So we are going to find the function's value and the derivative's values at pi over 6 all the way down. So we just want to plug pi over 6 in for each of these functions and see what the value is, all the way down to the fifth derivative. Okay, so y of pi over 6, that means cosine of pi over 6, which is root 3 over 2. Y prime of pi over 6, that's negative 1 times sine of pi over 6. Sine of pi over 6 is 1/2, so we get negative 1/2. Y double prime of pi over 6, negative root 3 over 2. Y triple prime of pi over 6 will be 1/2. And then we're going to start getting some repeats here. Cosine of pi over 6 is root 3 over 2. And then negative 1/2. So those are the building blocks for the coefficients. We just have to remember that once we get to this second order coefficient, we've got to divide by 2 factorial, and then divide by 3 factorial, and then divide by 4 factorial, and then divide by 5 factorial, ad nauseum. So our p sub 4 is a function, so we can put it of x. And we start with the first evaluation, so the value of the function, so that's going to be root 3 over 2, minus 1/2 times x minus the center. So there, so far we have p sub 1. That's p sub 1. The value of the function, and then the derivative multiplied by the shift. The center is pi over 6, so we're shifting to the right pi over 6. That is p sub 1 right there. To get to p sub 2, we keep on trucking. So we're going to have minus root 3 divided by 2, but then divided by 2 factorial, multiplied by x minus pi divided by 6 quantity squared. There's p sub 2. The best quadratic approximation, and we just keep on going. So we can then go to the next term, so the third derivative, so we get plus 1/2, but now we're going to divide by 3 factorial. We have x minus pi over 6 raised to the third power. So there's p sub 3. See if I can move this stuff over a little bit. And then we're going to do that again. So let's see if we can get our fourth order term in here. So the fourth order term, we're coming down to the fourth derivative. That's plus root 3 over 2. So we're going to have plus root 3 divided by 2, all divided by 4 factorial, multiplied by x minus pi divided by 6, all raised to the 4th power. So there we have it. That is p sub 4. That is our fourth order approximation. It's completely fine not to simplify this stuff. These coefficients, it's easier, in fact, when you look at the coefficients to see the pattern if you don't simplify them. Once we get past p sub 2, we rarely simplify things out in here. I mean, if it's super easy, then go ahead and do it, but you do not have to in general. If it's super easy, it's not a bad thing to do, but don't spend a lot of time simplifying the coefficients. So it lets us see the pattern. So p sub 5, all we're going to do is take p sub 4 and just add one more term. That term will be negative though, so we'll have a subtraction instead of an addition. So it will be negative 1/2 divided by
5 factorial.
5 factorial multiplied by x minus the center, all raised to the 5th power. There's p sub 5. So if you graph these things, it's going to look just like what we saw earlier today, where you have the cosine graph, and then at pi over 6, it's going to match exactly, and then as you go further and further out, it's just going to start wrapping itself around the curve. And if you did go to infinity, you would have what we call a Taylor series. And Taylor series, all you do is go like this, plus dot, dot, dot. Now you have a series. The pattern stays the same. And that Taylor series for cosine will exactly equal the function. There will be no error if you use the entire series. It will match exactly. Okay, so this says approximate the given quantities using a Taylor polynomial with n equals 3. So that's a 3rd order Taylor polynomial. So that means go down to the 3rd derivative. So let's do this one, and then I'll let you guys try the next one. So, once again, start with the function. Function that we have is tangent of x. And then if we want to get down to the 3rd order approximation, we need the 3rd derivative. So we're going to go y prime, which is secant squared of x. And then y double prime, which is 2 secant of x to the 1, multiplied by the derivative of secant, which is sec tan. So we'll get 2 sec squared tan as our 2nd derivative. And then our 3rd derivative will be ugly. We have to use the product rule. We're thinking of this as first function and second function. There's first function, there's second function. So product rule, first derivative, second. Derivative of tangent is secant squared, so first derivative second becomes 2 secant to the 4th of x. So that's first times derivative second, plus the derivative of the first times the second. The derivative of the first is 4 secant of x to the 1, bring down the 2, subtract 1, multiplied by the derivative of secant, which is secant tangent, multiplied by the second function, which gives us tan squared. Product rule. And then we evaluate each of those at our center. Generally, we want to have our center be something that we know how to evaluate these things at easily. When we look at this number in here, we want to approximate tangent of -1/10. We want to pick an x value that's very close as possible, to -1/10, for which we can evaluate these functions. The obvious choice is 0, right? That's close to -1/10, then we can evaluate all of these at 0 quite easily. So we will pick 0. So we're choosing a equal to 0. So that's going to be our center. So now we evaluate each of these at the center. So y of 0 is tangent of 0, which is 0. Y prime of 0, secant of 0, which is 1. Y double prime of 0. Y double prime of 0? What's that going to be?
0.
0, because tangent of 0 is 0. So that's going to be gone. And then the triple prime evaluated at 0. The tan part's gone. Tangent of 0 is 0, so this term would be gone.
2.
Secant of 0 is 1. 1 times 2 is 2. So there are our coefficients. Or at least the building blocks for our coefficients. We have to do the division by the factorial thing when necessary. So our approximation that we are building is p sub 3. P sub 3 of x, it's a polynomial. It starts with 0. Let's put it in just as a placeholder. So it's going to be 0 plus 1 multiplied by x minus the center. Maybe well, yeah, I guess I'll put the 1 in there. It just feels funny. Okay, 1 times x minus the center is 0. And then plus 0 divided by 2 factorial times x squared. And then plus 2 divided by 3 factorial times x cubed. So that is our third order approximation. Third order approximation. And because they're asking us some stuff over here, we are going to simplify this a little bit because they are asking us to do some substitution. So if we simplified this, we'd have x plus 1/3 x cubed. So there is our simplified p sub 3, simplified third order approximation. Okay, so now they want us to compute the error. The absolute error just means the absolute value of the error. So we can plug this into the calculator to get a super accurate approximation. This is going to be a less accurate approximation. Remember, when you type that into your calculator, you are getting an approximation. It is not giving you an exact value unless you have a super fancy computer algebra system. Right? An exact value would have square root of something over something. Right? If it's just a big decimal expansion, that is an approximation. So when you type that into your calculator, you're getting a super accurate approximation, but it's still an approximation. That's not exact when you type that in your calculator. It's an approximation. This will give us a slightly less accurate approximation. So let's go ahead and see what happens when we substitute these things into our graphing utility here. So let's get out of Dodge. And we want the tangent, so this is going to be our super accurate approximation. It will be accurate as far as the Desmos screen can be read. And then our polynomial approximation, our Taylor polynomial, is going to be x. So we can do this in a lot of ways. You know, we could define this as p sub 3 if we want to be fancy. P sub 3 of x is going to be x plus 1/3 multiplied by x cubed. So there is our polynomial. And then p sub 3 of 0.1 is equal to, did I not do that well? What happened here? We don't want that.
You forgot an equal sign on the second one.
Ah, thank you. Thank you. Equal sign there. There we go. So, how come our sign is off? Why is our sign off?
It's not when I plugged it in.
Oh, I might be in the wrong. Am I in the wrong units for the angles?
I'm in degrees and I'm not getting what you're getting.
Plugged a positive 0.1.
Thank you.
Ah, there you go.
Yeah, we want to be in radians. There we go. There we go. Yes, thank you. All right, so there is our business. Yeah, definitely want radians though, not degrees. All right. That makes sense to everyone? Now, they did ask for the absolute error, so the error is going to be the difference in these two values, and then with absolute value. So the error, we would take the super good approximation, and I just forgot the minus sign again. Super good approximation minus our pretty good approximation. And then we would take the absolute value of that. So we do this, put an absolute value bar around that guy. Really? You're gonna be that finicky? Finicky. Control X, get inside, control paste. So there is our absolute error. So absolute error is just the difference between the super good approximation and the less good approximation, our Taylor polynomial, and then take the absolute value bars, or make it positive. So we went out very little, not very far, third order derivative, and our error is very small, super tiny error. And that's how a lot of these common functions are. You don't have to go that far out to get accuracy pretty quickly. All right, so you all try this one. So same idea, go out to the third order. And what do you think the center should be here if we're approximating natural log of 1.05? 1. Because 1 is the closest value for which we know, what the natural log of 1 is. So take your derivatives and do it the same way we just did that one. And let me know if you have a question. I can come and give you a tip.
Exactamente. Eso sí me acuerdo. No, sí. Del derivativo. No tengo idea. Saca un XP, ese X. Menos, ese X saca menos. Mira, bola de como X. Sale de derivativo. Ese, no, sale L. Ah, you're crazy.
We'll be right back. Why is this?
You need to put that in like.
Dice que usa ese de loading high high load.
¿Cuál es Rick? No recuerdo.
Es como f de x, vamos a ver qué es sobre la g al cuadrado.
esa mamá.
La regla.
Pero es solo. Y mira. Y si tú pones. Mira, si tú pones también es igual a.
You don't have to worry about the number.
Pero es más fácil. El derivativo pone esto aquí y le suma 1.
Can you do that?
Yeah, because you used to do power roll and then change.
Wait.
No.
Pito.
¿Qué huevadas estás? No, he wants to do it like to the zero.
No, pero cuando se
Si quitan la
But
es
I
negativo.
want to use the
So you would get wait, you'd get 1, -1.
Para arriba las celdas de
Sí, pues lo que está diciendo él. Pero así es como se hace.
yeah, but
Yeah, but you need to make it.
Oh, you're supposed to put an X. Okay,
Yeah.
I got the idea.
Y ella tiene la idea. Por fin.
I get things my head.
Has anyone got their polynomial yet? Close.
Maybe.
I'll start taking derivatives. It's going to take a minute to take all these derivatives.
Ya está.
¿Hasta qué? ¿Hasta
2X
qué nos dijo que nos
menos.
fuéramos?
Es, ¿qué? Sí, es 3 nomás. Son 3. El último es el tercero. Esta es Sofía. A ver, ¿cuánto? Sí, lo hice bien.
It's in my house. My calculus study has practiced different.
Ya, no mires la pantalla, no vale.
So those should be your
No vale.
building blocks for your coefficients. the value of the function and its derivatives. And our polynomial, our p sub 3 of x will be 0 plus 1 times x minus 1.
Pero que no tenga la raíz.
So that is the tangent line right there. That is the best linear approximation. And then we go to the second derivative, minus 1. Here we have to divide by 2 factorial. And then it's going to be x minus 1 squared. There is your best quadratic approximation. And now to get to our best cubic approximation, we're going to add the 2, but we have to divide by 3 factorial. And then we have x minus 1 cubed. So that is our best cubic approximation. Yeah?
So the third derivative 1/2.
The third derivative down here.
No, because you multiply.
So this negative 2 gets multiplied by the negative 1 to make it positive 2, and then we subtract 1 from negative 2 to get negative 3.
Isn't that just 1 over x?
This is 1 over x.
Oh, that becomes 1. I see.
And so it's easier with that to leave that exponent negative up there for the purpose of derivatives. Can you take care of him?
Ayúdalo, que queda revision.
That all make sense?
Al final.
So that is our third order approximation. Again, you don't have to simplify these coefficients. It's pretty easy to do it in this case, but you would never square out this x minus 1 and cube that out. That would be ridiculously complicated.
No, no, that's
But if you wanted to,
No.
you could kind of leave, if you're, and it's so funny because normally we're super uptight and we want you to simplify everything. This is the one case where we really don't care. That would be a simplified form that would be fine, of course, but. Okay.
What?
What?
No, nothing.
What, nothing? Okay. So you could simplify it just by canceling that 2 over there. So then let's figure out the approximation versus the super approximation. So go back over to Desmos. And let's do log of 1.05. Okay, so there is our super good approximation. And then let's get our polynomial in here, which is x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed. That look right. And then we want 1.05 here. Down here we want natural log 1.05. 1.05. All right, so there we have it. There is our approximation using the Taylor polynomial, 0.0487, blah, blah, blah. There is the super good approximation from Desmos. There is the difference, so that is called our absolute error. Absolute error is just the difference between our reasonably good approximation and the super good approximation from a calculator or Desmos. But both are approximations. Any step there that you are wanting to ask about? Once you see the pattern of coefficients, it gets pretty fast.
I have a more general question. So, what question are we answering with this? Like, we are getting the approximation.
So what we are doing is understanding how to find error. So our polynomials are giving us an approximation. We are using one that we can already type into a calculator. So the purpose in this case is just to sort of understand how you would calculate error. In general, you don't know this. Like when you go out in the world and you solve a differential equation, and most solutions to differential equations are infinite series, which get truncated into Taylor polynomials, but you don't know what the actual convergence is to, so what we're going to do is come up with a way to approximate the error like we did with the alternating series. With the alternating series, we approximated the error by looking at the first unused term, and that was a good approximation of the error. Here we can find a really good estimate for the error, but in the real world, you're going to be estimating that error with some sort of process.
So that, it's not a series, it's a
Polynomial,
polynomial.
Taylor polynomial,
So what is our domain? What can x be?
any real number.
Okay, and it would, it doesn't
But we
matter
want-
how far we are on the center?
We want to be close to the center because the closer you are to the center, the better the accuracy.
Okay, but we don't know, like, at what point you're gonna be off.
So if we were to graph it, and we went out to p sub 3, we could see where it starts to peel away from the curve and not be as accurate. But that would be a visual thing. What we do know is that the further and further and further out we go, we will get more and more and more accurate. It's just that we'd have to look at the visual to see where that accuracy is kind of diverging.
And that x that we will put in there will give us the result of natural, so it's calculating the natural log of that x, basically.
So it's calculating natural log of 1.05.
Okay, so what x can be any number, then what are you gonna get?
So if you wanted to estimate 1.10, you would plug in 1.10. So this will be accurate, this will be reasonably accurate if you're close to 1. So if you plugged in 0.8, 0.8 is close to 1. Any number that's a little greater than 1 or a little less than 1 would give you a polynomial value here that's going to have a very small error. Now if you plugged into this polynomial 10, then you're far away from the center, so that accuracy, that error would be much bigger. So we always are trying to build our polynomial from a value that we know that is semi-close to whatever we're trying to approximate. So the error gets bigger and bigger as you get further and further from the center. So does that make sense?
Yes.
And it's interesting. You could plug in a 2 and just see what natural log of 2 is and how the error is bigger. Oh, if you were trying to approximate natural log of 2, what do you think the best center would be? E. E would be the best center because 2.7 is closer to 2 than 1 is to 2. And E is a number that we know how to evaluate in here. So if we were trying to approximate natural log of 2, we would go through this process. 1 is pretty close, but 2 would be even closer, or E would be even closer. All right, so now when we are dealing with these polynomials in general, we have this situation which looks very similar to what we did with series. Right, with series, we had, instead of a p sub n, we had an s sub n. S sub n was the estimate for the sum of the entire series. And instead of a function, we had s. We had a series that converged to, say, S. That's what the F is representing. And then we had an R sub n. And so R is the same thing here. It's just the remainder. It's the difference between the function and the polynomial. And for us, we had the sum minus the approximation was the remainder when we dealt with S sub n also. It was similar. And that's what we just did with our error. We found the absolute error by taking the absolute value at a particular point. We could find the error. So here is the remainder in general. So if you were to go off and do numerical analysis and some more advanced engineering type stuff, advanced math stuff, Taylor's remainder theorem is super prevalent in all sorts of error analysis. Because again, most of the time, when you're using data and you get a differential equation, the solution is an infinite series. That's what happens in the real world. So in the real world, we don't know what it converges to, but we still need to figure out some gauge on the error. And you can still get some gauge on the error, just like we did with the alternating series. The alternating series, we had all these alternating series. We don't know what they converge to, but we know that the first unused term gives us a good estimate of the error. Here's how you would do it in general. This looks a heck of a lot like the first unused term, right? Our coefficients, when we did our Taylor polynomial, the next term in our Taylor polynomial would be the n plus first derivative evaluated at the center divided by n plus 1 factorial multiplied by x minus a to the n plus 1. Right, that would be the next term. If we do our nth order Taylor polynomial, if we went one more term, that would be the next term. What is the only difference between that term and this? There is one difference. What is it? C. This is evaluated at A. It's evaluated at the center of the series. The remainder is evaluated at this mysterious C that you cannot find. If we could find it, we could get the exact remainder, but we cannot find this C value. This C value is some number that is between x and a. It's just some number. We cannot find it. So then you say to yourself, well, okay, well, if this is exactly equal to the remainder and we can never find this C value, what good is it? And the answer is down here. Just like with the alternating series test where we took that first unused term and it wasn't, exact, but it was close enough. This is how close enough works in this scenario. Okay, we can't find the C to figure out what the value of this numerator is, but what we can do is take this function's derivative and we can bound it. So we can take a look on this interval right here between x and a. We can say, well, okay, we have an x value, we have an a value. Let's just see when that n plus first derivative is biggest or furthest away from the origin. When is it biggest in magnitude? And if we take that bound for that next term, we can then use that to get an approximation of the error. So the error will be less than or equal to this. So we use sort of the bound, and that's just like with the alternating series test. We took that first unused term, and it was an overestimate for the error. But same idea here. Now, this process is super tedious. And we are not going to, I will not test you on this. We're talking about it. There's some problems in my math lab that have to do with this idea. But this won't be, you won't be tested on this because it's super, it can be very time consuming. It can be it's very technical. When you get into higher level courses and you have to deal with error, you will come back and wrestle with this remainder theorem, especially in differential equations or partial differential equations classes. You will deal with the remainder and, figure out good, efficient ways to bound the n plus first derivative. For us, our focus on error is really going to be limited to the alternating series. But it becomes a big issue as you go on in engineering, this concept of error. And so we want to at least give you some insight into how this is going to be created, how you can find an estimate for the error. Okay, so that is where we're at. Any questions up to this point on finding Taylor polynomials, on calculating absolute error? Anything you can think of that you want to ask? Any random stuff before we get into power series in detail? So right now we're dealing with Taylor polynomials. Next we're going to go to the series. All right, well, let's take a look at series then. So, we're going to look at a couple of examples. The first series we are going to look at should look darn familiar. In chapter 10, we came across the geometric series. The geometric series is a type of series that you see out in nature all the time. There are many, many, many things that follow a geometric growth pattern. And we learned that if we had a numeric series, everything's a number, and we had a geometric pattern to it, which means there's a common multiplier. So R is called the common multiplier, the common ratio. It is how you go from one term to the next. You multiply by R. And moreover, we learned this very cool fact that the sum of a geometric series is A divided by 1 minus R. In this case, A happens to be 1. So a geometric series had this nice, concise formula for the sum of an infinite number of terms. And we found that convergence only happened when that common ratio had a magnitude less than 1. We, in this chapter, are going to change our perspective. We are now going to flip left side to right side to left side, and we're going to change the R to an X. When you look at this, you don't think of a function. You think of that as just a number. Plug in R and you get a number. It's not a function. Well, we are going to turn it into a function. That is a function. That is a hyperbola that is shifted and reflected. You know 1 over x. And you know how to shift and reflect. So this is now a function. And you've now written this function as an infinite series, as a power series. So now you have this function written in expanded form right here as a power series. So our very first series is really a series that we were already familiar with. All we're doing is changing this numeric value of R over to a variable. And we can say that this function will converge to this series as long as x is somewhere between -1 and 1. So this is just a reformulation of something we've already done. It's a geometric series. All right, and so this is what we want to do in general now. We want to be given a random function and find this. This would be the Taylor polynomial, if you stop it. And if it keeps going, it's a Taylor series. So if you were to do what we just did on the last 4 problems, if you were to take this y value and start differentiating, plug in 0 for the center, you would build that same exact series that we actually calculated in another way in chapter 10. So there are many ways to come up with the power series for a particular function. The power series will turn out to be unique regardless of how you got to it. One way is that constructive process that we just went through earlier today. Take a pile of derivatives, build those coefficients, that's going to build your power series. That's not how we generated this one, but that's how you could generate it. If you take this function and its derivatives and start plugging in the center, you'll get those terms. So that's a building block power series that we're going to use to get to other power series. You can also build power series by taking derivatives of known power series or integrals of known power series. So one power series can lead to another by integrating everything or differentiating everything. So there's lots of ways to create power series. This one will be one of the most important ones, the geometric series. All right, so when you have a power, now that geometric series was centered at 0 because there was no x minus a. It's understood that it's x minus 0. So the center was 0. So in general, if you have a power series centered at a, there's some things happening with that power series centered at a. When you look at the center down there, that's the, oops. When you look at that center, the values of x for which there is convergence are going to be surrounding the center. So if there are values of x that give you a convergent series, they will surround the A. You cannot have sporadic x values that cause the series to converge and then others in between that cause it to diverge. All of the x's that give you convergence will be grouped together in an interval. So this interval is called the interval of convergence right here. And the radius of convergence is half the interval of convergence. Radius of convergence makes you think of what geometric object?
Circle.
A circle. We don't see any circles. The reason it is called a radius of convergence is that if you allowed for complex numbers, so in other words, if you were in the complex plane instead of the real line, so if we're over in the complex plane where these are reals down here and these are imaginaries up there, you will actually get a disk of convergence. So whatever the center is, if the center is some imaginary number, say right there, you will end up with a disk of convergence instead of an interval of convergence. For us, being lowly real number folk, we're down here. If this is our A, that circle of convergence is going to be around there, and us in lowly Calc 2, we're just focusing right there on that little piece that's on the real line. When you get into complex analysis, you get to up the ante and jump off the real line and get into the imaginary numbers. It's complicated enough imagining plugging in real numbers here. As soon as you start plugging in complex numbers there, your brain starts to melt. We can imagine computing an infinite sum when those are real numbers based on what we did in chapter 10. But once you start throwing complex numbers in there, it's really unsettling. So we are going to be focusing on this scenario, but that is why it's called a radius of convergence, because actually it's a disk of convergence. We're just ignoring the imaginary parts. Okay, so those are some pieces of terminology. Now, what is interesting is that when we calculate this interval of convergence, there are going to be many different options based on the endpoints. So you can have all of this convergence from negative r to r, or whatever we want to call it, from the left side to the right side. But then the endpoints have to be tested separately. It is possible to have convergence where all the yellow is here, and convergence at the left, convergence at the right, or divergence at the right and divergence at the left, or one converges and one diverges. Anything can happen at the endpoints. So we are going to see as we build our process to find first the radius of convergence and then the interval of convergence, we're going to have to do this tedious work at the endpoints and test those endpoints. And if you were so unfortunate to be dealing with the complex numbers, the same thing holds. You'll get convergence inside here, and then anything can happen on that boundary. All sorts of weird garbage can happen on the boundary in terms of convergence and divergence. So we have to just be aware of that. All right, so let's pause here. I'll leave this slide up. We'll take our 10-minute break. Then we can talk about how do you find these nice x's? How do you find these friendly x's that actually give you convergence? Let's see here. That.
Okay.
Huh. There we go. Here's here. So the series that we see before our very eyes is centered at A. And C sub k just represents the random coefficients. Now, not every power series is a Taylor series. So a Taylor series comes from a Taylor polynomial where we started with a function and we start differentiating and building the power series for it. But not every power series has a common function that it comes from. Right? If you start writing down, a power series is just an infinite series where you have the powers of x, and if you have coefficients that have no pattern to them, you are not going to find a common function whose derivatives are going to give you those random coefficients. So here we're thinking about a random power series. So those c sub k's are, random coefficients. Could be a Taylor series, but not necessarily. So there are three things that can happen here. You can have, which we saw with sine and cosine and e to the x, you can have an infinite interval of convergence. It can converge for every single real number. And if that's the case, we say that the radius of convergence is infinity. So if your series converges no matter what x you plug in, you've got all real numbers converging, then your interval of convergence is minus infinity to infinity. Your radius of convergence is infinite. The case that's the most complicated is this one, that your radius of convergence is some positive number. Then you build this interval. So the interval, you've got your a value there, and then you're going to have a minus r and a plus r, like that. So this is the most complicated piece because you can calculate capital R pretty easily, you'll see. But then, like I mentioned a minute ago, these endpoints you have to test separately. So this is the most complicated part because there's two extra steps. Test the left endpoint, test the right endpoint. And then another kind of boring case is this one. Every series will converge at its center, but if that is the only place it converges, very boring, the radius is 0, because it only converges at one number. There's no extra x's for which it converges. So boring case, but in your mind, make sure it's clear that this series converges at A. Isn't there only one non-potential, one non-zero term? Because if you plug in A for that x, you get A minus A, which is 0. So if you're looking at an expanded power series, like we've seen x minus 1, x minus 1, x minus 1, x minus 1, if you plug in a 1, everything disappears but the first constant. So every series will converge at its center because when you plug in the center right there, when you plug in k equals 0, you just get c sub 0. That's the only term that would not necessarily be 0. All the other terms have to be 0 at the center. So every series converges at its center. Okay, so down here they're just giving us an example that you can have a radius of convergence down here of 2. All 4 of these intervals have a radius of convergence of 2 and a center of 4. So we're going to calculate the radius of convergence first, and that's going to help us get these goalposts. So in this case, the 2 and the 6 are the goalposts. But then we have to figure out, do we exclude with a parenthesis, or do we include with a bracket? We have to test those separately. All right, well, how do we find this stuff? Dun, 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 the ratio test. Sometimes the root test. Ratio test, 90% of the time, the ratio test is how we calculate capital R and figure out our goalposts, figure out the endpoints for our interval of convergence. So we'll go through how to do that with the ratio test. And then once we have the radius of convergence, then we're in one of these 3 cases. And if we're in the bottom case, then we have to test the endpoints. All right, so our 3 cases. Let's go. Let's do our first analysis of a random power series. What's the center of that power series?
1.
1. So it converges at 1 for sure. Center of that power series?
10.
10. So it converges for sure at 10. Because all the terms are 0, except possibly when you plug in 0. In fact, this one, the value is still 0, right? If you plug in 0, 0. Oh no, what's 0 factorial? I factorialed wrong. What is 0 factorial? No. 1. 0 factorial is 1. We'll talk about that later. That's neither here nor there for us. 0 factorial is 1 though. 0 factorial is 1. Okay, so let's do the calculus though. This is our a sub k right there. And we are going to use the ratio test. So the ratio test, we're going to take the limit as k goes to infinity of the absolute value, and this is going to look real familiar. Okay, so we are definitely needing absolute value bars now because there's an x. X can be negative 5 million or negative 12, or like x is some number on the real line. So we definitely can't just erase absolute value bars now. Quite frequently with the infinite series of numbers, we saw that there was often places where it was always positive. When you look at a general power series, you can never assume the x's are only positive or bigger than 1. There's always going to be some negatives to deal with. So we leave the absolute value bars. So same way that we did this back in chapter 10. So we're going to replace the k with k plus 1. So we're going to do that in the bottom. Now in the bottom, we do not need an absolute value bar because the denominator is positive. So we have k plus 1 factorial. So there's a sub k plus 1. A sub k plus 1 is that. And then if we divide by a sub k, we've done this enough that we know that we are going to have this. We are going to use the reciprocal multiplied by the reciprocal of a sub k. Dividing by a sub k is the same as multiplying by the reciprocal. And we've seen this quite frequently with the ratio test. It's the thing we love about the ratio test. There's so much cancellation. Let's look at the k factorials first, and we see that, oh, there's a k plus 1 left in the bottom. Because k plus 1 factorial is k plus 1 times k factorial. So we know that. It's going to reduce to just k plus 1 in the denominator. And now when we look at that factor of x minus 1, we have k factors of x minus 1 down below. We have k plus 1 factors of x minus 1 up above. There's one extra one up top, so all of them cancel except for one that's in the numerator. And we must keep the absolute value bars because x could be negative. X minus 1 could be negative. All right, so then we're there. Now this limit is based on k. It is not based on x. So that numerator has nothing to do with the value of the limit. Right? There's no k in the numerator. This limit says we are going to let k go to infinity. Not x, k. So, in other words, this absolute value of x minus 1 is constant with respect to k. And it does not change as k changes. There's no k in it, so it does not change as k changes. So this all boils down to absolute x minus 1 multiplied by the limit of 1 divided by k plus 1 as k goes to infinity. And what is this limit? And what's 0 times anything?
0.
0. So we get 0. So that limit is 0. So now we ask ourselves, just like in chapter 10, ratio test, root test, geometric series. Those three are linked forever. If the value of the limit is less than 1, we have convergence. So this tells us no matter what x you plug in, if you plug in 2 million or minus 2 million, does not matter. This limit is 0. That tells us that we have convergence for every single x, because this is always less than 1. So 0 is less than 1. Therefore, the radius of convergence is infinite, and the interval of convergence goes from neg-infinity to positive infinity. So that's the simplest case when we have convergence everywhere.
If you want to write a few terms of this series, so x remains the same.
X is a variable,
Yeah, but
so you could plug in any x you want.
yeah, if for example I want to write a few terms of this.
Mm-hmm.
So I decide, okay, my x is 5, and then I just change the k.
Well, if you were going to write out a few terms of this series, this is what it would look like. You would do, like, this would be, so this would be the first 3 terms of the series. Let's go 4 terms. So this would be the first 4 terms of the series. So there's the expanded form of the series. If you wanted to evaluate it at 5, you would plug in a 5 for each of these. And then you don't know, does it converge or diverge? You would have to do a test on that. So if you do plug in a 5, then you could see if you recognize a pattern. The only way we can test for convergence, we would have to have an a sub k. So you'd have to then, if you plug in your 5, you would then have to figure out a formula for the a sub k and then do the ratio test on it. What this is telling us is if we do the ratio test with the x in it, it's telling us it doesn't matter. This limit's always 0, which is always less than 1. So no matter what x you plug in here, you will have a convergent series. If you plug in a 5, if you plug in a 10, if you plug in a negative 12, no matter what x you plug in, this will converge. Because that's what this says. This says that the ratio's limit is always 0, so it's always less than 1, no matter what the x is.
And are the terms getting smaller or bigger in this?
Smaller. That denominator is factorial, grows really fast. The numerator is polynomial. So we know that factorial grows faster than any polynomial. So those terms are going, and we know they have to go to 0 if there's convergence. We know that the divergence test says if the terms don't go to 0, then you have to have divergence. So yeah, those terms are all going to 0. How about this one? Well, let's see. So same idea. We're just going to do the regular old ratio test. The limit is k goes to infinity. Absolute k plus 1 over absolute k, a sub k. Now we see that k factorial in the numerator, so we should be very wary. We should be expecting the exact opposite of our fringe cases. This is the other fringe case. The one fringe case is where it converges everywhere. The other fringe case is where it converges only at the center. And then we'll get into the ones that are a little more interesting. So k plus 1. All right, so we have k plus 1 factorial up here. That doesn't have to be in the absolute values, but I'll just leave it in there for now. So there is a sub k plus 1. And then a sub k in absolute value is that. And once again, we have our factorial cancellation. We know k plus 1 factorial is k plus 1 times k factorial. So we know that we're going to end up with a k plus 1 in the numerator. And again, that's positive, so we can pull it out of the absolute value. And once again, we see a pile of factors of x minus 10 below and a pile above. There's one extra one above, so we end up with just one factor of x minus 10, and it's in the numerator. So we have that. Once again, that x minus 10 factor has nothing to do with k. Has nothing to do with k, so it just pops to the front as a multiplicative factor. And we have x minus 10, which for any particular x is just constant. If you plug in x equals 15 or 12 or 100 or 1,000,000, that's just a constant. And we know constants don't affect limits, whether this limit's going to converge or not. And what is the limit of k plus 1 as k goes to infinity? Infinity. So we're here. And then we ask ourselves what we ask ourselves every single time we apply the ratio test. When is that less than 1?
Never.
Never. Infinity is never less than 1. So this is less than 1. Never. So you can put a line through it. So that means that the radius of convergence is 0. The only number for which it converges is the center. So you can say that there is an interval of convergence, which is really a degenerate interval. That degenerate interval is just a single value of 10. So it's not really an interval, it's a degenerate interval. It's just a point, just a single number. All right, so those are the two fringe cases, the two cases that are the easy cases, if you will. Although sometimes the easy cases invoke a little more mental questioning than the others. So let's do one of these. So here we have an x to the k over 5 to the k. It's also an alternating series. We, with power series, are always going ratio test or possibly root test. So, and you could use either in this case. Let's go ahead and use the root test for this one just because I see that the root test would work nicely. We've got a power of k on the outside here. So the root test looks just like it did in chapter 10. We let k go to infinity, and it's the kth root of the absolute value of a sub k. So the absolute value of a sub k is going to ditch the switch. That thing is going to be gone. No more switch when we take the absolute value. Now the absolute value bars we still need though for the x's. So when we take the kth root of this, we are going to end up with the absolute value of x divided by 5. Do you agree? So the first thing is that absolute value gets rid of that. And then the kth root of x to the k is just x. And the kth root of 5 to the k is just 5. But we still need the absolute value bars around the x. Right? Because we have a root here, everything inside's got to be positive. Keep the absolute value bars around the x. All right, so there's our root test. Do you see any k's there?
No.
No. So absolute x divided by 5 is constant with respect to k. So this, we all know that the limit of a constant is itself. So this limit is that. Okay? Now we do the same thing we always do with the root test or the ratio test. We take our limit and we compare it to 1, right? For a root test or a ratio test, convergence is when the value of that limit, whether you call it rho or r, you now ask yourself, when is this less than 1? That's what we want to know. When's that less than 1? Some x's will make that inequality true. There's other x's that will make it false. When you look at it, you see that if you plugged in a 1, it would be true. If you plugged in a 10, it would be false. So for some x's, that inequality is true. For some, it's false. So here's where we go. So this tells us that the absolute value of x has to be less than 5. So we multiply both sides by 5. This tells us that our radius of convergence is 5. And our interval of convergence has goalposts at -5 and 5. We don't know what happens on the left side or the right side yet. We don't know if we need a parenthesis on each side or a bracket on each side. We don't know yet. But what we do know is this is centered at 0. Right? It's not x minus 2 or x plus 3. It's just x. So centered at 0. And this interval right here, you can rewrite it like this. This compound inequality tells us this. That's what that compound inequality tells us. That x is between -5 and 5. So -5 and 5 are going to be the end points for our interval of convergence. Half this interval is 5 units. When you have x isolated on the left like that, that's always going to be your radius of convergence. But now we need to test our endpoints. So here's the hard part. Here's the time-consuming part. We have to figure out what happens at those two endpoints. So here's what we do. So we are going to test the endpoints now. So we are going to plug in x equals -5 and test. Does the series of numbers, does the numerical series that we get from plugging in this -5 and this 5, do we get convergent series? Let's find out. So we go back to the original series. We've got an alternating series. Okay, we know how to use the alternating series test. We're going to plug in -5 for that x. So we get -5 to the k over 5 to the k. Let's just write both of these first forms out. So if we plug in -5 or 5, these are the two cases that we get. So we just take the x, turn it into a -5, take the x, turn it into a +5. These are numerical series. We've done these, chapter 10. Let's first simplify. So this top one can be simplified. It's a little bit more work than the bottom one, but this numerator can be, we can peel it apart and have a -1 to the k and a 5 to the k, distributing that exponent. And then in both, we see that the 5 to the k's will cancel. All right? So this series down here is simplifying to -1 to the k times 1. That reduces to 1. This one simplifies to, let's see, what is -1 to the k times -1 to the k? -1 to the
2K?
2k, good. Add the exponents. And the 5 to the k, 5 to the k, that's just 1. All right. What is -1 to the 2k? What is -1 to the 2k? Think about it. What is -1 to the 2k?
Always 1.
Always 1. Right? -1 to the 2k, you can do a power to power. You can do it -1 to the 2, all to the k. Well, -1 to the 2 is +1, so then you have 1 to the k, which is 1. It's always positive. So this series boils down even further to just that. Okay? And this one, usually we would, if we leave the, usually we would just write this one as -1 to the k. This series up here, does that converge or diverge?
Converge?
What would it possibly converge to?
1.
So you're telling me that if you take 1 and add it to itself an infinite number of times,
Oh.
that would be a bad job. Right? You're not going to make a lot of money. I'm going to give you $1 every day, but you're still going to end up with $1 after 10 years.
But there's no K's in there.
There's no k's. So what is the value of a sub 0? 1. What is the value of a sub 1?
Oh, because we're adding them together, so we take
So a sub 1 is 1, a sub 2 is 1, a sub 3 is 1. Right, this series, remember this symbol means sum. So this, if you were to write it in expanded form, it's going to look like this. It means that for every value of k, you have an a sub k that's equal to 1. That's what that says. And that clearly diverges once we talk about it. So what is the explanation? What's the justification? What test?
Divergence test?
Divergence test, exactly. So the limit of a sub k is the limit of 1, which is 1, and that is not equal to 0. The divergence test says if that is not equal to 0, then you have divergence. Okay. Now this second endpoint, what do you think there?
That's going to converge to 0.
So let's see. Let's take a look at the expanded. When in doubt, going to the expanded form of some of these is really helpful. And this one started at 0, so we can put a 0 here. Doesn't really matter. We know that if you ditched the first few terms, it changes nothing. It's either going to converge or diverge still. So if you start with 0, this is 1. What about when you plug in a 1?
Minus 1,
Minus 1.
plus 1, minus 1, plus 1, minus 1.
Okay, does that converge? No!
What?
So remember, so these are two cases that are super easy to get squirrely in your head. Remember, for a limit to exist, the values, we need to, the partial sums need to approach a single number. So if we start looking, S sub 0 is 1. Oh, I shouldn't call it sub 0. Sub 1. S sub 1 is 1. What's S sub 2?
0,
0. What's S sub 3?
1.
1.
Doesn't
S sub
converge.
4? 0, etc. So the sequence of partial sums does not approach a single number. Right? The only way a limit exists is if the sequence of partial sums gets infinitesimally close to some single number. So what we have here is oscillation. The partial sums are oscillating. So the sequence of partial sums will not converge. And in your mind, you should be thinking that same thing. You think, okay, I'm at 1. If I subtract 1, I'm at 0. If I add 1, I'm back. You know, you're just bouncing around. You're not getting closer to a number. So some of these little fringe cases can be, you want to think about them carefully.
So do we have to do a different test there?
No, so what we can say, does the a sub k go to 0?
No.
No. So here we can say that a sub k, we can do the same thing we did above. We can say the limit of a sub k, and this a sub k, whether you take its absolute value or not, it does not matter. If you take the limit of negative 1 to the k, as k goes to infinity, this is not equal to 0, therefore you have divergence. So the easy justification there is to say that it fails the divergence test. The terms aren't going to 0. Terms aren't going to 0.
And we can't just plug those numbers into the absolute value of x over 5. It's less than 1. Because that gives you the same answer.
Say that again right here.
Yeah, so if you just plug in negative 5 there, you get 1. So it diverges, and then you.
So so when we look at those endpoints, this is inconclusive with the endpoints. Remember that if you get a 1, the test is inconclusive.
Oh,
So
it's
that's why we're
inconclusive,
looking
okay.
deeper. So the ratio test says less than 1 converge, greater than 1 diverge, but if you get equal to 1, it's inconclusive. And so for these two particular cases, 5 and negative 5, it's inconclusive. So that's why we're looking at them individually. And so what we've learned then here is that both of these endpoints have divergence. So our interval of convergence will be that. So our interval of convergence is going to be excluding both endpoints.
Should that be positive 5?
Yes, that's positive 5. Thank you. Yeah. Okay. So now when you look at this thing, if there was no x to the k, if this was a numeric series, if there was no x to the k, it would be an alternating series that converges or diverges. If there was no x to the k. So if we had negative 1 to the k, making it alternating, and just a 5 to the k in the denominator, would it converge or diverge? Converge. Because for an alternating series, the only rule is that the terms have to go to 0. If the limit is 0 and it's alternating, you're going to have convergence. So alternating series are they're relatively easy to analyze, because as long as the a sub k is going to 0, it converges. It will pass the alternating series test. All right, so let's take a peek at this one. So we're going to do the same thing that we did above. Let's go ahead and use the ratio test. ratio test is usually where we go with these things. So the ratio test, we're going to take the limit of the absolute value of a sub k plus 1 divided by the absolute value of a sub k. And as soon as we see those absolute values, we know right away that we can ditch the switch. That thing is gone. We're taking the absolute value, so it's taking away that minus right there. Okay, so a sub k plus 1. That's going to be x to the k plus 1, absolute value, over the square root of k plus 1. We don't need an absolute value on that because it's always positive. Dividing by a sub k means multiplying by the reciprocal. So we're going to have root k over the absolute value of x to the k. So that's the limit we need to evaluate. So first, let's take a peek at the x's. All right, there's one extra x up top. So we're going to have absolute value of x up top. There's one extra x up top. Need the absolute value because x can be positive or negative. It's just some real number. And then let's kind of group the square roots together. So we have this. Now once again, that x, there's no k to be seen inside those absolute values. That absolute value of x is constant with respect to k. So it can come to the front. We can combine these square roots. And what is the limit of that square root piece of it? 1. So the square root function is continuous, which allows the limit symbol to go to the inside. So the limit goes to the inside. And yes, it's indeterminate. We have infinity over infinity, so you can either analyze it by taking L'Hopital's rule, take the derivative and the derivative, or you can say, hey, those are polynomials with the same power. The limit is the quotient of leading coefficients, 1 over 1, which is 1. Lots of ways you can do it. Divide by the highest power of k, whatever it is. So we get this. Absolute x times 1, which of course is absolute x. And now, we're at the end of our limit. We've reached the end of our limit. The ratio and the root test, once you get your limit, you ask yourself, when is it less than 1? So you ask yourself, hey, is this ever less than 1? Is it less than 1? Whenever it is less than 1, you have convergence, more precisely absolute convergence. And when it's not, we have divergence. So if you plug in a 5 here, you have divergence. If you plug in a half, you have convergence. If you plug in a quarter, you have convergence. If you plug in 10, you have divergence. But if you plug in 1, it's inconclusive. So we have to test. So from here, this is going to tell us that x is between -1 and 1. That's going to generate our radius of convergence. We can see the radius of convergence is 1. It's half the interval length, which is 2. So the radius of convergence is 1. The interval of convergence, we know the goalposts, but we don't know whether to bracket them or to put a parenthesis on one or both. So that's where we're at right now. So after the ratio test, we can calculate the radius of that interval of convergence. Now we have to, before we can actually finish our interval of convergence, though, we need to test. We need to do the hard part. So here is our test. We have to say, okay, let's let x equal -1. Let's let x equal 1. These are going to give us numeric series. Then we're going to go back to chapter 10, use our stuff from chapter 10 for the endpoints. So let's see. Plugging in -1. So we have -1 to the k multiplied by multiplied by -1 to the k again over root k. So this is going to be -1 to the 2k divided by root k. And -1 to the 2k reduces to
1.
just 1, right? -1 squared is +1. So this is going to be 1 divided by root k. Does that series converge or does that series diverge from chapter 10?
Well, this is the alternating series. So in that case, if you do the limit.
So hold on one sec. So not an alternating series, because that minus sign disappeared when we squared it.
Right. Yeah. Okay.
So what kind of series is it?
That's the series.
P series, right? It's 1 over k to the p. So that's a p series.
So the power is halves, which is less than 1, so then converges.
So p is equal to 1/2. That's how I know you know it's p series. Then you compare it to 1. You make your conclusion.
Therefore converges.
Therefore, it.
Oh, never mind. This is the P series. This is different from the ratio. So if it is less than 1, then that means it diverges.
Yes. Yes. Therefore, it diverges. All right, remember, P series is exactly the opposite of root, ratio, and geometric. Exactly the opposite. Root, ratio, geometric, less than 1 converges. P series, less than 1 diverges and greater than 1. And think about it, right? We saw with the improper integration that 1 over x squared converged, but 1 over x had an area that diverged to infinity. And 1 over x went to, the area went to infinity. Okay, so that means we now know for our interval of convergence that at -1 we have divergence, so a parenthesis. Now let's check out at 1. So at 1, okay, we have -1 to the k, and then 1 to the k, but 1 to the k is just 1, so we end up with -1 to the k multiplied by 1 over root k. Alternating series. Alternating series. Does that alternating series converge or diverge?
It's going to also diverge.
Remember the alternating series test, there's only 2 pieces. Does the limit of 1 over root k go to 0?
All right, there's 2 different tests when it goes to 0.
Alternating series, there's 2 parts. Does 1 over root k go to 0?
No.
Yes, it does.
As k goes to infinity?
Oh, yeah.
Yeah.
A constant
Right?
number when it goes to 0.
So 1 over root k goes to 0. Okay, so that's the first piece of the alternating series test, which is essentially the divergence test. If 1 over root k goes to 0, then we're we're inconclusive with the divergence test. The divergence test either finds divergence if the limit is not 0, but if the limit is 0, then we have to do more work. And the nice thing about the alternating series test is as long as that thing is going to 0, it's going to converge. The alternating series test just says this has to go to 0, and it also says that the terms have to be getting smaller. Well, if that limit's going to 0 and we don't have some weird crazy function that's going to 0 progressively, right? It's not some oscillating weird thing. This is going to, right? So, and with the alternating series test in chapter 10, you would be expected to show both steps. The limit of a sub k is 0, and a sub k plus 1 is smaller than a sub k. The terms are getting littler. But here in chapter 11, where we're just peripherally dealing with chapter 10, you should be able to just look at this and say it converges by AST. You don't have to do any deep, you don't have to say, oh, the limit of a sub k is 0 and a sub k plus 1 is less than a sub k. You don't have to do that here. So in chapter 11, we're going to just grab the easy tests from chapter 10 and just state them. The easy test being P series, divergence test, alternating series test. Okay, so we have convergence at that endpoint. So now we can finally complete our interval of convergence. So there's what we are looking for. The radius is 1, the interval of convergence is half open, half closed. It's clopen. Half closed and half open. All right, any piece of that you want to dig into a little deeper? So ratio test and root test, just like chapter 10. And then when we get to the endpoints, the things we typically see are P series, divergence test, and alternating series test. Those are the 3 things we see the most with endpoints. So you really want to get zeroed in on P series, alternating series, and the divergence test. And sometimes the divergence test can be a little sneaky. You look at that, and it just feels like it should converge because there's just a 1 in there. But you just have to remember what it means. Summation of 1 means 1 plus 1 plus 1, etc. So super easy to get tangled up on that at first look. All right, combining series. When one series is not enough and you want to add a little more fun, toss in another series. So if you have two series that converge, and more precisely, I should say power series. So a power series converges to a function, whereas a numeric series converges to a number if it converges. So we have two power series. They converge to these functions f and g. And as you would expect, as we've seen with limits and derivatives and integrals, if both of those converge and you add or subtract, the addition or subtraction will then yield convergence to f minus g or f plus g. That's very intuitive. Okay, number 2. Our power series have all started with, k equals 0 or 1 is very typical for all the series that we've kind of seen. And right here, they are saying if we have a power series that converges, so the C sub k series is converging to f, and you multiply it by a power of x, so x to the 3, x to the 5, you're still going to get a converging series. There's one subtlety here I need to point out, and it's not obvious. So they're saying that k plus m has to be positive. All right? If this series here did not start at 0 or 1 like we are very used to thinking it's starting at, it's possible that this starts somewhere else, so keep that in mind. It's also possible, they didn't tell us that m is positive here. Right? They did not tell us that m is positive. We keep multiplying by positive powers, but this one example here, they have not told us that this m is positive. They just say it's an integer. So if this was x to the negative 3, we have to be careful. Because if this starts with x to the 1, then you multiply x times x to the negative 3, you get x to the negative 2, which is 1 over x squared, which is not a power series. Right? Power series have powers, positive powers of x, or non-negative powers of x. So we have to be just a little cautious there. So this series is going to converge, as we might expect, usually this would be the case, to x to the m times f of x. But we have this one thing here. If x is 0, the series converges to the limit. And the reason is that this m could be negative. So let's suppose that our C sub k series started with x to the 3, all right? And then this x to the m was just 1 over x. So we have x to the 3 for our first term. We multiply by 1 over x. We still end up with a positive exponent, x to the 2. Everything is good. But we had a 1 over x in front, so this whole thing is not defined at 0. So we would have to take the limit here to get that value for when x is 0, because if we were multiplying by a 1 over x, it's not defined at 0, so we'd have to take a limit. Now we are not going to see this in any, that's not something I would put on a test, but just to be complete and explain why you have this intuitive piece, oh yeah, if we multiply by x to the m and that converges, it should converge to x to the m times f. Like that makes a ton of sense, but there's just one oddball case. If your coefficient, if you're multiplying by 1 over x, that's not defined at 0, so you'd have to take a limit. Okay, so, but 99% of the time when you multiply by a power, all you do is this. Multiply it by the function. Composition. This one's a little tricky. You're going to end up liking it. It's going to end up actually being pretty straightforward in the end, but when we first talk about it, it's going to seem odd. So if we have a composition, so we've got this guy is converging to f, and when we build the composition, so we're going to take this h function and we're going to put it inside of f. So instead of just f of x, it's now going to be modified. So that's going to be modified right there. And what is going to happen is that we are still going to have convergence, except the convergence interval is going to change. So if we have if we have the original series, converges to f, it's got its interval of convergence. But then if we do a substitution into f, that substitution is going to follow all the way through to the interval of convergence and modify it. It won't be as hard as it sounds. I promise. That part won't be the hard part. So let's try it. Geometric series. This one is one of the series you absolutely must know. That series is a building block series for a bunch of other series. So here they tell us we've got the geometric series converges for x less than 1. Now we want to find power series representations of this. Okay. Well, the first thing I see is that we have x cubed multiplied by geometric series. 1 over 1 minus x is the geometric series. So this is number 2 above. We have x cubed, and we don't have 1 over x. There's no 1 over x, so this is all kosher. So we have k equals 0 to infinity, x to the k. That's the geometric series right there. We're multiplying by x to the 3, and we kind of do what you think we would do. We pull it to the inside, and we have x to the k plus 3, and this is going to start at 0. There is our new power series. No funny business, because there's no division by x. So this is case 2, and we get that right there. So the interval of convergence is that. What do you think the interval of convergence is here? So interval of convergence, I'm going to tell you what it is, then we'll talk about it. So the interval of convergence does not change. It does not change. Let's think about why. So here is your a sub k. Okay? If you think about the ratio test, and you have your a sub k plus 1 over a sub k, you've really multiplied your a sub k and your a sub k plus 1 by k to the 3, and they both cancel. Right? When you go to form the ratio, both a sub k and a sub k plus 1 will just have an extra 3 powers of x, which will just end up canceling anyway. Or you can say, hey, well, a sub k plus 1 is going to be x to the k plus 4. And down in the bottom, you have an x to the k plus 3, and that's all going to reduce to just x. So multiplying by a power of x is not going to affect the interval of convergence, because those powers of x are sort of in both the a sub k and the a sub k plus 1. So multiplying by a power of x, as long as there's not division by 0, we're good to go. That is what we're going to have. That is the power series representation of this function. All right, now let's look at this one. This one deals with case 3 up there. This is the composition case that feels a little, feels like it feels a little wordy up here. So here's what we do. So all we're doing is replacing the x with x cubed. Right, this x, that x right there, turned into an x cubed. So all we do to build the new power series is do the same thing on this side. We've got the power series for 1 over 1 minus x. Replace that x with x cubed, we get this. Replace that x with x cubed on the inside. All right, and that we can simplify to just x to the 3k. Starts at 0. All right. So that is the new power series. That is the power series for 1 divided by 1 minus x cubed. Interval of convergence. There's our original interval of convergence. The original interval of convergence, if I expand it, is that. If we replace this x with x cubed, we have to replace that x with x cubed. So in this interval of convergence, we also have to modify it with a composition. we turn that x into an x cubed. When you have an odd power on an inequality, you can just take the odd root of all three pieces, and you're fine. So this inequality actually is not going to change. You can take the cubed root of all three pieces. So our interval of convergence here actually did not change. It is the same. But you can see, if this was an x squared, things would change. Because if we put an x squared over there, it would be a little bit harder to figure out what's going on. Or, if this interval of convergence was -8 to 8, and you took the cubed root of all sides, you get a -2 to 2. So it could change.
So then are we essentially, for this composition method, are we just essentially splitting the main function from the numerator, or like the, whatever you would call the, like, multiplier?
The h, the substitution piece.
And you would replace that with like x of k always, or what?
So so when you look at this up here, your pattern is 1 over 1 minus x. And so whatever is replacing that x, so whatever that x has turned into, you do the same thing on the inside. You turn that x into the same thing that this one turned into.
Okay.
And then the third piece is that then you also have to do that with your interval of convergence, that you turn that x into whatever it turned into.
So that x cubed is the h of x
Yes.
up there?
That's what's getting substituted into the f. Yeah. So the f is this, and then when you substitute in the x cubed, it replaces the x with x cubed here, and we're just saying, oh, well, you keep on going and replace it there, and you replace it there. We'll do another one of those, because those ones,
Okay.
they feel, in practice, as we do a few, you'll see that that they're not as bad as it sort of feels at first. Let's try another one here. So we're given a power series for ln of 1 minus x. Interval of convergence is a lopsided interval. Include the -1, exclude the 1. So it's a little different than the geometric series. So find the power series for these new functions here. So similar to the last one, we are taking x squared, power of x. The power is bigger than 1, so we don't have to deal with any division by 0 business. That just makes things more complicated. We don't need that right now. And now we're going to multiply it by the power series for ln of 1 minus x. So the power series for ln of 1 minus x is given. So here's our power series for that part of it. X to the k divided by k. And the interval of convergence is -1 to 1, including the -1. So it does not change. When you multiply by a power of x, that interval of convergence is not going to change. So the only thing we have to do here is simplify. One little simplification. That x squared can jump to the inside. This series will start at 1. We'll use our shorthand notation here. We know it's going to infinity. We already established it. Plug in the x squared. That's going to be x to the k plus 2 divided by k. And you can write your interval of convergence in several ways. I'll try to use different ways as we're going through just to get used to different notation. But multiplying by a power of x doesn't change the interval of convergence.
Is that -1?
That is -1, thank you. That is -1. All right, now we're going to do the substitution one again. So when we look at this new function was obtained from the original function by substituting x to the 4th in for x. All right, so the power series, we're going to do the same thing to calculate the power series form. That's a negative sign in front. And we have a series goes from 1 to infinity, and we're going to replace the x with x to the 4th. So we're going to have x to the 4th raised to the k divided by k. And if we simplify that, we're going to have the series starts at 1. That's going to be x to the 4k divided by k. And now let's look at our interval of convergence. So we have to do the replacement with x to the fourth in between -1 and 1. So we have that. Okay. Now we have to simplify that interval of convergence. And there's a couple of ways to do this. This tends to be a little subtle. Let me try to explain it carefully. Do you agree that x to the fourth is always always greater than -1? Right? X to the fourth has an even power. You plug in 0, you plug in 1, you plug in 10, you plug in -5, does not matter. This is always bigger than -1. Okay? So this side of the inequality is always true. So what really matters is that if the left side of the inequality is always true, the only piece that we have to really focus on is the right side of the inequality. Okay? This inequality here translates to this. Do you agree? So think about, so here is, let's look at a picture. So if we were to envision x to the fourth is something that looks a little bit like a parabola. We are looking to have it between -1 and 1. So the values are on the y-axis. And like we just said, x to the fourth, it's always bigger than -1. That part's always true. Okay? And we want to know what x's force it to be between -1 and 1. Well, as you start looking at these x's, when you go out to x equals +1, all right, that's going to correspond to this point up here. -1 is going to correspond to this point up here. We want it to be less than 1, though, not equal to 1. So we want to put parentheses on the -1 and the 1. Make sense? So you can do it visually, or you can kind of reason it out. But in either way, this is going to be our new interval of convergence. So we lost the point of convergence. We lost the -1. Think of it this way also. If you plug in -1 over here, what happens? What do you get inside that log? 0. Natural log of 0? Undefined. Natural log of 0 is undefined. Right? Natural log of 0, if you look at the graph of natural log, looks like that. Natural log of x not defined as 0. Natural log of 1 is 0. But up here, when you plug in the -1, what do you end up with on the inside? 2. Natural log of 2 is defined. Yeah. So that's also another clue. All right, let's take a look at one more slide. And actually, I don't want to look at this slide. Let's look at another slide first. For our final slide, let's go down here to, I want to give you some insight into looking at these series and how they are related. So I've broken them into 2 groups of 6. The first group of 6 is this group, and they're going to be based on the geometric series. So this is the geometric series. If you integrate the left side, don't you get that? If you integrate this, oh, it's log, but then you have to do a reverse chain rule and divide by -1. If you integrate the right side, integral of 1 is x, integral of x squared is x squared over 2, blah, 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 blah. So this is the integral of the geometric series. It's another power series. We would have to test the endpoints. Whenever you integrate or differentiate a power series, The inside of the interval, you still have convergence for if you differentiate or integrate. The endpoints, stuff can happen. So you would have to reevaluate at the endpoints. When you reevaluate at -1, you get convergence. It'd be an alternating series. This I refer to as the alternating geometric series. So if we come up to this geometric series and we do what we just did, if we replace this x with -x here, then we go through and we replace all those with -x, we get this alternating series. So I'll call that the alternating geometric. And it looks like a geometric, except it's got the alternating signs. Its interval is going to be the same as that one up there. This would be the integral of the alternating geometric. You integrate that, you get ln x plus 1. Integrate 1, you get x. X squared over 2, x cubed over 3. All right. Now, natural log. If we want to get a power series for ln of just x, not ln of 1 plus x, we have to do a replacement here. And so what we are going to do is that substitution thing. If we replace this x with x minus 1, the 1's will cancel and you'll get just an x. And if you replace all of these x's with x minus 1, you now have a series for natural log. And where is the center of it?
1.
It's right at 1. It's right where natural log crosses the x-axis. The natural place for the center. One last series here. So if you look at this alternating geometric here, imagine replacing the x with x squared. If you replace that x with x squared and all the way down, what is the integral of 1 over 1 plus x squared? Integral of 1 over 1 plus x squared. Integral of 1.
Tangent?
What kind of tangent?
Inverse.
Inverse tangent. Inverse tangent. So the power series for inverse tangent, we come up to the alternating geometric, replace that x with x squared. Where was that? Alternate right here. So replace all these x's with x squared. If you integrate this, you integrate that, that's now an x squared, so it's going to become an x cubed over 3. That's an x to the 4th, so x to the 5 over 5. And this integral of x is just 1. Bingo, there's your inverse tangent infinite series. Notice that there's no factorials in that one. So we will see that this is identical to the sine infinite series except for the factorials. There's going to be a lot of parallels. But all right, we'll stop there. Good luck doing some homework before Thursday. And remember, your worksheet for chapter 10 is due Thursday night by midnight, which really means Friday morning. So I'm not going to do anything after midnight. Related to grading. It might be related to math, but not related to grading.
I already got it done, so basically I'm just gonna have to drop off the